What's up, Algebros? In this video I'm going to go ahead and show you how to derive the library function called the cube function. Now this function is called the cube function because of how we operate on the inputs. Any particular value of x that we decide to plug in, we're going to have to cube it in order to get the output. And that's where I'd like to go ahead and start. So let's go ahead and fill out this table. If x is chosen to be -2, to get the output we'd have to take -2 and cube it, which of course that gives us -8. And that gives us our first point to plot, -2, -8. So let's go ahead and do that. Plugging -1 in, we'd have -1 cubed, giving us -1. And our second point to plot is -1, -1. Plugging 0 in, we have to take 0 and cube it, and we get 0. So this graph is another graph that goes to the origin. Plugging 1 in, 1 cubed, gives us 1, so 1, 1. And then plugging 2 in, 2 cubed, gives us 8. So our final point that we're going to plot, just based on this table, is 2, 8. Alright, so the more points you have, the more accurate your graph will look. But having these is good enough information to help us infer the rest of the graph. What I'm going to do is connect all these points together. I'm going to start with -2, -8. We're going to snake our way through those 3 points that are kind of bunched around the origin. And then we will continue through the point 2, 8, and I'm going to extend beyond it. I'm really sorry for my shaky hand here. And at -2, -8, we'll go ahead and extend the graph so that this end of the graph is going towards -infinity, whereas the end of the graph in quadrant 1 is going up to +infinity. Alright, so there's my graph. Not the most beautiful graph, but I think it's enough to help us get some of the details of the cube function. Alright, the domain for this function is going to be all real numbers. One reason being is the rule for the function x cubed, there's no place to divide by 0, and there's no even roots that we'd have to worry about taking the even root of a negative number. So since we don't have to worry about division by 0, nor negatives under even radicals, the domain of this function is all real numbers. Likewise, this graph does extend horizontally forever and ever. An easier way to kind of look at that is you look at the piece in quadrant 1. This piece is shooting off to +infinity, and although it's going up pretty sharply, it is kind of going to the right at the same time, just not at as much of a rate as it is going vertically. But the only way for that to even happen is if you're using all the positive x values. Likewise, in order for this piece to be the way it is, we'd have to be using all the negative x values on the x-axis, and of course we're also using 0 to get to 0.00. The range for this function is also all real numbers. You can infer from the graph that there's no smallest y value. The center of the graph shoots down to -infinity, nor is there a largest y value because the end in quadrant 1 points up to +infinity. Likewise, the graph is fully connected, so every value from the y-axis is serving as some sort of y-coordinate for a point on this graph. So the range is all real numbers, so -infinity to +infinity. A couple ways you could determine the next result is visually and analytically. Visually, this graph appears to have origin symmetry. If you look at the piece in quadrant 1, now keeping in mind this is not the most accurate sketch due to my human error, but if you were to take this piece in quadrant 1 and reflect it across the y-axis and then the x-axis afterwards, it would perfectly line up, theoretically perfectly, line up with the part that's in quadrant 3. And vice versa, if you were to mirror the part in quadrant 3 across the y-axis and then the x-axis, it should perfectly line up with the part that's in quadrant 1. So, based on the visual stuff, this would be an example of an odd function. Now, from the analytic standpoint, I'd like to go ahead and compare 3 expressions, f of x, f of -x, and -f of x. Of course, f of x is just x cubed. F of -x requires us to plug -x into x cubed, giving us -x quantity cubed. Simplifying that gives us -x cubed. Negative f of x tells us to take the original function, x cubed, and multiply it by -1. Of course, that simplifies to -x cubed. And you can see that f of negative x's expression is exactly equal to negative f of x's expression. In other words, negative x cubed is equal to negative x cubed. So since f of negative x equals negative f of x, this function would be an odd function. Okay, so that would kind of be like the analytical way of showing that. As for increasing or decreasing, if you trace your finger along this graph from left to right, you'll notice that you just continually go up on it. And so the x values that would force that to happen for this graph would be all of them, negative infinity to positive infinity. So this graph is increasing using all of the values from the x-axis. We would say that it's increasing on the set of real numbers, kind of like the geeky phrase for that. So what does that mean about decreasing? Well, it's just not applicable. We don't have any parts of this graph that are decreasing. All right, and that's all the deets for the cube function. Thanks for watching. Let me know if you have any questions.